Hi, my name is Alejandro Sanchez, and I'm part of the CAC Cognition Group, along with Amo Kulati and Long Juan. Over here, I just want to show that the end-to-end pipeline of the self-supervised learning. On the right side is just a typical picture of how the flow is, of how we pre-train our encoder. I'm just going to skip next, since a lot of you guys already know how that works. And I want to talk about a little bit about our data sets. Our data sets here on the right side are just some pictures that we captured from the ImageNet data set. And also we wanted to show how there are specifically some images of birds in nature, which were actually one of the ones that we were mostly focused on. And so we went ahead and we went into ImageNet, and we specifically filtered pictures of animal, birds, and natural categories to train our encoder with. We also merged with CPAR 100, Caltech 101, and Caltech 256, Pascal VOC, Oxford Flowers 102, and MS Coco, only the images. Over here is just some pictures of our dyno runs. We use Dyno V1 for our encoder, and I just want to say that in this pre-training curves demonstrates stable Dyno V1 optimization behavior. The epoch progression increases early with training steps, indicating consistent data loading and uninterrupted training. The stepwise loss exhibits an initial transit phase with higher variance, followed by a smooth gradual decrease as training progresses, reflecting the alignment between the student and the teacher networks. Inherent to self-distillation, the average training loss decreases monotonically throughout the pre-training, suggesting successful convergence without representation collapse, and indicating that the learned presentations continue to improve over time. And the MAE run was similar as well with the dyno, but we did see that our dyno run, as you can see in this picture, that the accuracy was actually better than our MAE run, and we decided to go on with our dyno run. Finish.
For linear probe training, we froze the encoder and trained a single linear layer on the features. We benchmarked IJEPA, MAE, and Dyno V1. Our findings show that Dyno V1 was the superior architecture for our specific constraints, leading to higher accuracy when we applied the linear classifier. Our approach has three main components. SSL pre-training, in which we took the Dyno V1 model pre-trained with a ResNet 18 backbone on a large corpus of about 1.25 million images, mentioned earlier, for about 100 epochs. Secondly, we did domain adaptation at the representation level. For each evaluation set, we continued SSL training using the same self-supervised objective on the train splits for about 50 to 100 additional epochs. And lastly, we combined the models into a single, basically the base model plus the domain adapted models in an ensemble-like strategy. So some key advantages include improving robustness under domain shift. It captures both general and domain-specific features. It also avoided unsupervised fine-tuning on target labels and minimal architectural and computational overhead. As you can see in the table, the Dyno plus ResNet 18 and domain adaptation configuration was our best performer. Looking at the birds data set, Dyno without adaptation hit about 16.6% accuracy. With our domain adaptation, that jumped to about 18.7. MAE, on the other hand, struggled with 15.86 and 10.61 respectively. In conclusion, we had a few takeaways. So we learned that training curves show stable optimization and expected behaviors across the multiple runs. MAE reconstructions qualitatively validated learned structures beyond raw loss values. Linear probing provides a clean protocol to compare representations. And then other things like the architecture matters quite a bit. Adaptation actually helped boost feature robustness, and then using the ensemble of models actually helped us gain a few percentages. And here are the references for our work. Thank you.